Welcome to the final exam, question number 36, and it says to select the incorrect statement about strength design of reinforced concrete. And this is going to be a pretty in-depth, short answer because I want to give it just as much as I can, so I'll attempt to. We start with A. The code provisions assure that yielding of the tensile steel will occur before the failure of concrete, and that is definitely correct. It's true, so it's not the right answer. And I'm going to go through this real quick, and hopefully you can get a decent idea of what is exactly going on. So let's say that this, and this is obviously not scale. We're going to assume this is your, taking a look at the cross section, this is a stress diagram. And in concrete design, what you do is you're going to have a tension side, which tension is going to equal the area of your steel times your yield stress of that steel, which is usually 60 KSI. Area steel, you get your number of bars times the bar area. So that is going to form a force couple, and instead of this compression wedge, so you really don't want to think about it being this wedge down here, because that's not how it is. And then in your compression side is, instead of looking at this wedge, you actually get this compression block of depth A. And instead of doing the wedge, this is what assumed for design. And this is A right here. This is A, and your compression equals 0.85 F prime C, which is your 4 KSI or whatever. And this 0.85 just comes from the assumption. They figured out what is a good assumption to make instead of this wedge, and it's 0.85 times this A. And then they said that F prime C, your B, which is your width of your member, and then, or width of the compression block, let's say that, times A, your depth. All right, and that's going to be your moment, this distance right here. Let's change colors again. If you take either one of these times this distance, that's going to be your moment. The distance right here. That's going to be your internal moment. All right, and in compression design, since right here in the tension, here's your neutral axis. Let's call it NA. And that moves up and down depending on how much steel you have. If you have more steel, that means it will push this compression block down because you have more steel to stress, I guess. And it means more of this compression concrete can be engaged. So you need to hold this at the strain equals to 0.003 for design, and that pretty much matches up with your yield stress. Or yeah, you don't want to go over this. If you do, then your concrete will crush, and you will have a catastrophic failure if you go over this. So this is in concrete design, you have to keep this, and that's where you can deal with your reinforcing steel. You want your reinforcing steel to yield. You want to yield this. You want to go over that before you yield your concrete. And I hope that makes sense. And here's another quick thought process of it. You have a beam, and if the concrete crushes, the steel will just buckle, and you'll fail. It'll be a catastrophic failure. And and the reason this is, if you fail the steel first, if you yield this steel first, the steel has here. Let's see. You have to do this. You have to do stress strain curve of steel. And if you remember, you have this is a constant slope. You have the elastic region, and then once it starts yielding, it goes into the plastic region. and then it will do something called strain hardening, and then it'll fail altogether. And so let's say you overstress, you yield the steel. Well, it's right here. So that steel is starting to, it has failed for design. You have failed that steel, and it starts to lengthen, and it lengthens. And then when you let go of it again, it has this permanent, it follows the same slope right here. It follows that same slope, and it comes down. So you will have permanent deformation. Right there is going to be your permanent deformation. And you will be able to tell in your steel. You'll look up and say of a building, hey, that, the ceiling tile's cracked, and the tile on the floor cracked, and you can tell there's a big old, a dip in your floor. Hey, we need to fix it. But since the stress right here went up, it didn't have a catastrophic failure. Now, if you went all the way up here, obviously that's a catastrophic failure, because the steel cannot hold that. But the good property about steel is that it will start lengthening. It's something called strain hardening, and the steel actually gets stronger, and it's able to hold those higher stresses, but it had to deform so much to do it. So instead of, you have this case, the beam will, you take that load that overstressed it, the beam will look like this. It will, and that's obviously pretty overstated. I doubt it's going to deflect that much, but just to show a point, and it will stay like that. You might remove that huge load. Let's say you have a pack of elephants go over your bridge, and you remove that load, and you say, oops, we failed. This is a failed bridge. We need to replace those. We overstressed it. So what was our, that was a long way to go, but I hope you kind of caught on to what we were looking at there. So in the end, you want to overstress the steel. You do not want to overstress the concrete before you overstress the steel. So, all right, let's move on here. And you say that, I like your hat, Liam. All right, B, it says the depth of the rectangular stress block A is less than the distance from the extreme compression fiber to the neutral axis. So neutral axis to extreme compression fiber is right here. So it is less than that. So that's not the right answer. And then C, the concrete stress at the extreme compression fiber at failure is equal to F prime C. And we do not want it to, that's an incorrect answer. So this is true. This is not true. And that's going to be our right answer. And we do not, remember the whole point of concrete design is you want to, well, you don't want it to fail at all, obviously. But if it does fail, it says at failure, you want this to fail first. And if this equals F prime C, then that means this will fail first. We do not want it to equal F prime C. It should equal less than that. So we designed for that. And in the code, it actually makes it so it's, I think, 0.75 of the actual, they call it a balanced condition. It would be balanced if this equation equaled this equation. And usually what you're going to do is, it will be 0.75 of this equals that. I may have that backwards, and I don't want to think about it right now. In any case, you want this to be, the concrete to be stronger than the steel, and you want that to go first. And they have that in the code, like I said. So C is not true, and therefore it's our correct answer, but let's go over D and make sure we're right. For a singly reinforced beam, which we have, singly reinforced, I guess we haven't really gone over that, is this when you have it down here. And don't have compression steel up here. The steel is assumed to resist all the tensile stress, and the concrete is assumed to resist all compressive stress. And like I said, that's true. So it's not the right answer. And our answer is C. As I said over here, you're not counting on any concrete down here. And this is your compressive block. And you are everything, yes. Sorry. Everything you're assuming is your tensile stress in your concrete. So that's your moment arm, is the C of the compression concrete up here, and the T of the steel reinforcing down here. So once again, our answer is C.